Hello, Dr. Mashburn here again, and we're going to continue our lectures about the bone and the skeletal system. And so today's lecture is going to focus on bone development. So how do we actually make the bones? Let me see if I can get this. Whoops. Having some technical difficulties. Sometimes that happens. Just hang on just a minute. All right, bone development. All right, so first of all, what is bone? And so we've talked about bone being osseous tissue, and it's made of something called a matrix. So bone is made up of a matrix, and if you'll remember, bone is a type of connective tissue. So all the connective tissues have some kind of a cell that makes it, and then there's some kind of a matrix. So remember, cartilage has your chondrocytes. You have your blood, which has blood cells, and plasma is your matrix, and in cartilage, the cartilage is your matrix. So in bone, you have your bone-producing cells, and you have a bony matrix or a hard matrix. And so this matrix is an osteoid substance. Remember, anytime you see osteo, that means bone. So osteoporosis, we're going to talk about holy bone, which is something you can get as you get older. So osteoid means bone. So it's an osteoid substance that's secreted by osteoblasts. Remember, osteoblasts are the builders. Okay, they build the bone. And in addition, this osteoid has collagen, and collagen, remember, anytime you hear the word collagen, think strong. So it helps give the bone strength. And it has something called hydroxyapatite, not hydroxycut, so it's not a weight loss medicine or anything. It's called hydroxyapatite, and it's a calcium salt. And so that's what makes bone hard. So we take calcium from the blood and put it into the bone, and that gives the bone its hardness. Okay, so hydroxyapatite is just the way we put the calcium into our bone. Now, bone is not just a hard substance. It also has living cells. Okay, so bone has the osteogenic stem cells. It has osteoblasts, which are your building cells. It has osteocytes, which are just mature osteoblasts. And then we have osteoclasts, which can break down bone. So osteoblasts are what take calcium out of the blood and put it into the bone. And then osteoclasts take the bone and break it down and then send the calcium out into the, I didn't write that very well, out into the blood. Okay, so osteoclasts break it down. So remember, it's a hard substance, but it has living cells as a part of it. It also has nerves and blood vessels as well. So when we think about bone development, it occurs in several stages. You have your bone formation, and we call this osteogenesis, and then ossification. And so genesis means the beginning, so beginning of bone. And then ossification is the hardening of it, or the calcification. It's making, when you lay down bone, a lot of times it starts off, it's like cartilage, and then that's got to turn into a hard bone, so that's the ossification. And that's going to begin around the second month of development. And so once your bones are formed, so you're born and you have all your bones, okay? Now those bones need to grow. So you have bone formation inside the uterus during fetal development. And then once the baby is born, then from there until adulthood or early adulthood, puberty, you're going to have bone growth. And then you're going to have bone remodeling and repair. So all throughout our lives, our bones are constantly remodeling and repairing themselves. I mean, if you're 40-something years old and you break a bone, you've got to be able to repair it. So that's going to be going on all your life. Also remodeling. If you wear a brace, so maybe you've got some curvature in your spine or maybe braces, you're remodeling your bone. So your bones is going to do this all your life. So you form your bone, you grow your bones, and then you keep them healthy by remodeling and repairing them. All right, so this bone formation or osteogenesis, ossification. So what I'm showing you here, this is basically a picture inside the uterus, and you're seeing basically the kind of the cartilaginous template of these bones, and then you're seeing the bones form. So where it's kind of clear, that's where the bones haven't ossified yet. They haven't become hard, so they're kind of transparent. They're still that plasticky cartilage membranous looking stuff. You have two ways of making bone. You have what are called endochondral bones and intramembranous bones, and so that's what you're seeing here. These are endochondral bones, your long bones here, and your intramembranous bones are forming these bones around your skull. And so in both cases, you form connective tissue first, okay? And then you harden that or ossify it. And you can ossify it in one of two ways, something called intramembranous ossification or endochondral ossification. So one requires a membrane and one requires cartilage, and we're going to talk about the different types of ossification. But in both cases, you lay out connective tissue down first, and then you ossify or harden it, put the calcium in it, and turn it into bone. You start to see this ossification at about 8 weeks of gestation, and generally what happens is you have your connective tissue there first, and then bone cells migrate to that connective tissue. All right, and then these bone-forming cells, they start to secrete that osteoid, which is the organic compound of bone, which makes it hard. So that osteoid will calcify, becoming hard, and then you're going to start to reshape and remodel that bone. Okay, so that's kind of the last step. So you lay down the cartilage or the membrane, you put in the bone forming cells come in, they put down the calcium, that makes the bones hard, and then you're going to reshape them and remodel them. So that's the general steps of bone formation. So let's go into each type and talk about what's going on. So the two types of ossification are intramembranous ossification and endochondral ossification. Remember, chondrocytes, cartilage, so that kind of gives you an idea. Membranous thinks membrane. So in your intramembranous ossification, you make a fibrous membrane first. So your template is a fibrous membrane. And this is how we make the flat bones, like the clavicles and the sternum and the cranial bones. So flat bones use intramembranous ossification. Endochondral ossification is you lay down hyaline cartilage first. That's your template. Then the bone cells come in and they ossify. And so you're going to have to break down that cartilage, and then you're going to ossify what's left, and you're going to form bone. And I'm going to show you how that works as well. And most of our skeleton is formed that way. Okay, so that's your two forms. So let's start with intramembranous ossification first. So we're going to, this is bone growth from the inside out using a membrane template. Okay, so step one, so we have our membrane. So here's our fibrous membrane, all this purple stuff that you see. Our osteoblasts are going to come in, they're going to migrate in, and they're going to start to secrete this osteoid. And so you're going to have this osteoid being secreted around these osteoblasts, and it's going to calcify or get hard, and that's going to trap those osteoblasts. Remember those lacuna? So now they're trapped, and once they become trapped, they become osteocytes, those mature bone cells. So that's what's left inside the bone. Now this next step is you get some new matrix made, and you have blood vessels come in and kind of randomly come in and help to reshape that bone, and you get the formation of spongy bone. All right, so a new matrix is put down, forming the spongy bone, which is a way for the blood vessels to go inside the bone. And then the last step is you have to, this isn't very strong. You've got a bone made of just spongy bone. That's not a very strong bone. You need to give it a compact bone ring around it. So the last step is to make that compact bone outside. So again, you have a periosteum, and your osteoblasts are going to come in, and they're going to start making compact bone just outside that spongy bone. So they're going to make a ring of compact bone around the spongy bone. So again, this is what happens in those flat bones like in your skull. So you have a small level or layer of compact bone around a kind of a thicker layer of spongy bone. So you made the spongy bone first. So inside, you made the inside first, and then you came and made the outside. You put down the compact bone. Okay? So you inside first, and then outside. Now endochondral, a little bit different. This time you're going to use a cartilage template. So it's hyaline cartilage. Remember, you have three types: hyaline, elastic, and fibrocartilage. The hyaline cartilage is what we use to form our bones first. It's the template. So you lay down your template. So this is looking like it's going to be a long bone, okay? And so then we make a bony collar. That's the first step. So you start to make a little bony collar around the outside of the cartilage. And then the cartilage on the inside and the diaphysis, it starts to calcify and deteriorate. And this is going to make that medullary cavity. So once there's a space there, blood vessels and cells can go in, and you can start to make that spongy bone. So that would be step 3. So you have a hole, blood vessels go in, bone cells go in, and you start making spongy bone. Then the osteoclasts come in. It's like you build it, then you break it down. The osteoclasts come in, and they kind of break down most of that spongy bone and actually leave a cavity. So that way you have an area for your bone marrow to form. So now the osteoclasts come in and kind of make a big space for your bone marrow. And then the last thing you got to do is make the compact bone. So the last step, just like in the intramembranous, is to make the compact bone. The osteoblasts come in and they form compact bone around the articular surfaces at the epiphysis, the proximal and distal epiphysis, and also at this epiphyseal lines. Okay, so you're going to get compact bone put down there. All right, so that's going to be the steps. And again, we're not going to go into a whole lot of detail. You're going to see this kind of as an ordering question or all that apply question. Just know the difference, the kind of a compare and contrast. What's the difference between intramembranous versus endochondral, and which bones are made using intramembranous and which bones are made using endochondral. Okay, so your flat bones are going to be intramembranous, and all other bones are endochondral. So once you form the bones, now we need for them to grow. So you've got all your bones made. You have all 206 bones, and now you're going to be born, and those bones need to get bigger because now you're going to go from infancy to childhood through adolescence. So everything's got to get bigger. Muscles have got to get bigger. Organs have got to get bigger. Bones have got to get bigger. And so they grow in 2 ways. They've got to get longer and they've got to get wider. So interstitial growth, that means you're increasing the length of the long bones. Okay, so your femur is going to get longer, your humerus is going to get longer, all your long bones have got to get longer. But then you also have to get some widening of your bones. You don't want a skinny little, if you're born with a femur that's this long and this skinny, as you get to be an adult, it needs to be a little thicker and a little longer, so it's a stronger bone. So appositional growth is the increasing of the width of the bones, so they get longer and wider. And we do this using our osteoclasts and osteoblasts. There's a balance between them, osteoblast building bone and osteoclast breaking it down, and they work together to remodel and reshape and grow bones. All right. So when we're talking about long bones, we're going to talk about the growth of bones at the epiphyseal plates. So remember, you have your long bone and you have a line of cartilage at that epiphyseal plate, and that's where your bone is going to grow. Now, when you think about the way this works, I've got this picture here, and you have a zone of chondrocytes, okay? The epiphyseal line, the epiphyseal plate, is a zone, or your growth plate, is an area of chondrocytes, living chondrocytes. It's between the epiphysis, the end of the bone, and then the diaphysis, or the shaft of the bone. So that's that line right here. So that's a line of living chondrocytes. And they're alive and active until your epiphyseal plates close, which in females is around age 18 and in males around 21. So after your growth spurt, so you know as you've been going through adolescence and now you guys are in college, for you girls, somewhere around maybe 10th or 11th grade, you haven't grown anymore. You're as tall as you're going to get. And then males, you may still be growing. You may still have a couple of years left to go because females typically hit their growth spurt and then stop growing around 18, and then males around 21. So the way this works is you lay down the cartilage first. So this is going to be this step here where I have mitotic. Remember, mitotic is actively dividing cells. So they're dividing and they're making lots and lots of cartilage. That's step 1. So this is what this is. Okay, so I'm putting that cartilage down. And as those chondrocytes get older, they start to die off. That'd be step 2. Okay, and then you get these osteoblasts come in, and they're going to start to calcify that cartilage. So you're going to get calcification of the cartilage and replacement of that cartilage by the osteoblast with a bone matrix. So that calcifying cartilage is going to start to break down. The osteoblasts are going to come in and fill in the spaces that are left by that dying cartilage with osteoid and turn that into bone. And so this is happening around the epiphyseal plate, allowing the bone to get longer. So it grows at the epiphyseal plate between the epiphysis and the diaphysis, and the bone gets longer. All right? So what this would look like, if you look at an X-ray, you'll actually see this would be the epiphyseal plate right here. So if you're looking, and right here. So if you're looking at a long bone, so here's your diaphysis, the shaft, and then this would be the epiphysis. This is the epiphysis, and this is the diaphysis. Epiphysis and diaphysis. So you'll actually see a space. If you're looking at an adolescent or child, or before they've hit their mature, and before they've hit their growth spurt, or after they've had their growth spurt and they're now a mature adult and they're not growing anymore, you're going to see an actual space there because the cartilage isn't picked up on the X-ray, so it looks like a gap. Now, if you take an X-ray of a mature adult, that's going to be fused, so the cartilage is no longer there, so the epiphyseal plate has closed. So an open growth plate, you can actually, it looks like the two bones are separate. So to kind of give you a hint, so if you were to be a criminal investigator and you came across a set of old bones in the woods and they had all the muscle and all the tissue was all gone, and so let's just say you found a humerus and it was intact, all the way intact as one solid bone, you would be able to know, if you knew a little bit about bone growth, that this is probably an adult. Okay, now let's say you found a humerus, and so you had a diaphysis, and you had a little end of the diaphysis, but there was a little piece kind of separate, and like the ends had fallen off. That would tell you that that was an immature human, so either a child or a teenager, because the cartilage that was holding the two ends together, the diaphysis and the epiphysis together, epiphyseal cartilage, the cartilage that was allowing you to have bone growth, it has deteriorated, it's rotted away, and the bones have fallen apart. So you can tell if someone has matured and reached their maximum height once that epiphyseal plate closes. All right, so now once your bone grows, you've got to remodel it, and we have what's called appositional growth. And so again, appositional growth is where the bone gets wider. And so what we're looking at here is showing you how here's your cartilage, and here's your cartilage here. So the bone is growing on the ends, so it's growing at the two epiphyseal or epiphysis on the two ends, and also at the epiphyseal plate. It's getting longer and longer and longer. But as the bone gets longer and longer and longer, it has to be reshaped. So what this slide is trying to tell you, it's kind of hard to do this in two-dimension. It'd be easier in three-dimension, but I don't have a three-dimensional way of showing you that. But as the bone is getting longer, you have to reshape it. So if you had a bone looking like this, and now it's longer than it was, as it's grown longer and longer and longer, you've got to reshape the head and the two epiphyses. It would be what, it's hard to say, this is kind of hard to explain. You don't want to wind up looking like one big fat bone. You've got to kind of bring in bone and reshape it. It's kind of hard to explain, but hopefully you guys are getting it. So what this is showing is we're resorbing the bone here, so we're remodeling it, and we're adding bone here, so that the bone can constantly maintain that kind of curved shape as it grows longer and longer and longer. That's the appositional growth, the remodeling of the width. Okay, does that make sense? I hope so. You may need to look in the book on that one. It's hard to explain this in 2D. All right, so bone deposit. So bone deposit is where we put more bones, more osteoid, more calcium, hydroxyapatite, everything that we need to strengthen a bone. So we deposit bone in areas when a bone is injured or we need extra strength. So if you've ever broken a bone and the bone heals back together, you'll actually see it looks a little thicker. There's extra bone compared to what it looked like before. We've made the bone stronger. You'll also see more bone deposit in people that are overweight. Their bones are denser bones than people that are thin because of all the weight that they're holding. So this stress of additional weight causes the bone to have bone deposit. Also, if you look at a bone, and so let's just look, kind of draw a femur. Your femur has a trochanter, which is where your muscles attach. It's a thickening of the bone, so you're going to deposit a lot of bone in these tuberosities and processes and places where muscles attach. You need something strong there for the muscles to attach to. So bone deposit is where you need some kind of strength to the bone. But in order to do this, you've got to have a good diet. You've got to have vitamin C and D and A, calcium, phosphorus, magnesium, and manganese. And we're going to talk about some of these factors in another video, a separate video. All right, and then not only do you have bone deposit, but you have bone resorption. And this is when remember we talked about our bones act like a bank to store calcium. So this is when we want to take the calcium out of our bone and put it into our blood. So our osteoblasts, their job is to take an enzyme that will digest that organic matrix and allow that calcium salts to be converted to a soluble form that can go out into the blood. So bone resorption allows you to, if you're in a time of maybe poor diet and you don't have enough calcium in your blood to run your muscles and your nervous system, then even your blood clotting, when you talk about blood clotting, you need calcium for that as well. If you don't have enough calcium, your osteoclast will start to pull that from your bone, which is one of the reasons you need to maintain a high calcium diet throughout your life. So calcium is something that you need to keep in your diet by eating dairy, green leafy vegetables, or even a supplement if you need to keep. You don't want to there's only so much calcium in your bones. You don't want to keep pulling from that bank over and over and over again. You want to make sure you're getting enough calcium in your diet, because you're pulling that calcium from your bones, you're going to make them weak over time. Okay, so make sure you're getting enough calcium in your diet so that you're not constantly pulling it from your bones. All right, just a couple of little things I wanted to just throw in here. When you think about bones, the developmental aspect of the bones, when you're looking at an embryonic skeleton, it ossifies predictably. So when they're doing a sonogram, they can actually do a pretty good job figuring out the age of the skeleton of the fetus. I'm sorry, or of the child. So when you look at this, they can see the thickness or how the bone is, how the membrane and the cartilage is becoming bone and how it's ossifying. It's pretty predictable, so it gives them a good idea of how old the child is. But at birth, then most of these bones are going to be ossified, except for the epiphysis. Okay, so when you're looking at long bones, they're going to be solid bone. Don't worry about breaking a child's bone. Okay, so they've got hard bones, but the epiphysis, that's still cartilage. Okay, and we'll talk a little bit about bone breaks and some how you can have some damaging breaks if you break the epiphyseal line, and we'll talk about that when we talk about bone fractures. Just in case I don't, because sometimes when I'm talking in video I forget about things and I'll think about it earlier or later. So if you were looking at, again, an x-ray and you saw a long bone, okay, let's just draw a long bone. You've got your epiphyseal plate and you've got your two, the epiphysis, the proximal and distal epiphysis, and then here's your cartilage that's holding the two together. So think about an athlete. If you were to do something, a twisting motion or even a fall that separated your epiphysis from your diaphysis and separated out that growth plate, when they pin you back together and put you in a cast, you have to hope that cartilage, those chondrocytes, come back. Sometimes a break can damage those epiphyseal plates and the bone won't grow anymore. So that's the danger if you have a young child playing sports and they get injured. You want to make sure they didn't damage their growth plate, because it could turn out that the bone doesn't grow any longer. Okay, just in case I forget to mention that in a future video. Okay, so by the time you're 25, all your bones should be ossified. And so you've kind of got your peak bone mass in your 20s. So you guys are in your 20s, you've got a lot of bone. You want to maintain it by exercising, because stress helps keep your bones strong, and also a healthy diet. Because when you get into your 30s and 40s, your bone mass starts to decrease, okay? You start to have a pretty predictable loss of bone mass in your 40s. But this can change. It depends on obviously your genetics and your environmental factors and your diet and exercise, okay? But if you don't do anything, you will start to lose bone mass. As you get older, bone resorption outpaces bone deposit. So again, your bones get weaker. You're taking more calcium from your bones than you're putting into your bones. And then this is just a couple of random bone facts, just, just a freebie. We actually recycle our bone mass every week. We're going to recycle about 5 to 7%, so we're constantly building and rebuilding our bones. We completely replace our spongy bone every 3 to 5 years. We replace our compact bone every 10 years. So these osteoblasts and osteoclasts and osteocytes, they're working throughout your entire life, keeping your bones healthy and strong. And bone is the last thing that we're going to find of you. So if you're buried, that bone can last for thousands and thousands of years in a grave. So take care of your bones, because they're probably going to be the last thing that's found of you on this earth. All right, so that's all I'm going to talk about right now, and I'll see you in the next video. Thank you very much.